You do this almost every day. You drop a few cubes into a glass. They bob to the top. You don't think twice about it. But almost every other solid in the universe sinks in its own liquid. Ice is the exception. And the reason it floats is one of the strangest quirks in all of chemistry. Think about it. Melt a candle and drop the wax back in. It sinks. Freeze olive oil and drop it back in the bottle. It sinks. Solids are supposed to be denser than their liquids. Tighter. More packed. That's just how matter works. Except water broke the rule. To understand why, you have to shrink yourself down to the size of a single water molecule. 2 hydrogen atoms. 1 oxygen atom. Bent, not straight, like a tiny boomerang. That shape matters more than almost anything else in this story. Because of that bend, water molecules pull on each other in a very specific way. The oxygen side is slightly negative. The hydrogen side is slightly positive. Opposite charges attract. So every water molecule reaches out and grabs onto its neighbors. Chemists call this a hydrogen bond. It's weak compared to the bonds inside the molecule itself, but there are billions of them, all pulling at once. In the 1930s, the chemist Linus Pauling was one of the first to explain exactly how these hydrogen bonds worked, and why they gave water properties that seemed to break the normal rules of chemistry. His work helped explain something people had noticed for centuries but never fully understood. Here's where it gets strange. When water is liquid, those hydrogen bonds are constantly breaking and reforming. Molecules slide past each other, packing in fairly close. But when water freezes, something unexpected happens. The molecules don't pack tighter. They lock into a rigid, open, six-sided lattice, like a honeycomb frozen in place. Every molecule holds its neighbors at arm's length to keep the hydrogen bond stable. That open structure takes up more space than the liquid does. More space, same number of molecules, means lower density. And lower density means it floats. Ice isn't heavier than water. It's lighter. About 9% lighter, gently on top instead of sinking down. You might assume scientists fully cracked this mystery decades ago and moved on. They didn't. Water is still one of the most studied, and most argued about, substances in modern science. In 2009, the physicist Anders Nielsen and his team at Stockholm University published research showing that even liquid water isn't as simple as one uniform structure. It behaves almost like 2 different liquids mixed together, shifting between denser and looser arrangements depending on temperature. Why does any of this matter to you? Because if water behaved like a normal liquid, life on this planet might not exist at all. Picture a lake in winter without this strange rule. Ice would sink instead of float. Layer after layer would drop to the bottom. The lake would freeze from the floor up, not the surface down. Eventually the whole thing could turn solid, top to bottom, killing almost everything living inside it. Instead, floating ice does something remarkable. It seals the surface like a lid. That layer of ice actually insulates the water underneath, keeping it near 4 degrees Celsius, which happens to be water's densest, most stable point. Fish, insects, plants, entire ecosystems, survive winter under that frozen ceiling because of a quirk in molecular geometry. The chemist and water researcher Martin Chaplin, who has spent decades cataloging the unusual properties of water, has pointed out that dozens of water's behaviors defy what you'd expect from a simple molecule. Its high surface tension. Its unusual heat capacity. Its refusal to sink when frozen. Chaplin's research suggests water isn't just one exception. It's a whole list of exceptions, stacked on top of each other, that happen to make a livable planet possible. So the next time you drop ice into a glass, you're not just watching a cube bob to the surface. You're watching billions of bent little molecules lock arms with their neighbors, spread themselves out, and refuse to sink, because letting go of that space would mean letting go of the very bond holding them together. There's something oddly human about that. Holding your ground, keeping your distance from the people closest to you, and somehow that distance is what keeps the whole structure from collapsing. You dropped a few cubes into a glass. You still don't think twice about it. But now you know the whole ocean is floating on a rule this planet was lucky enough to get right.